Okay, so as I mentioned, our next rule deals with dividing, and this is the quotient rule. So maybe we have something in the form of u and v, like this. How are we going to do it? Well, we could put it to the -1, and we could, of course, do that. That would work. This is just another formula of way of doing this, and we'll actually show how we derive this. So, okay, so when a function is in the form of u over v, and where u and v are both functions of x, a small increase in delta x causes a small increase in u and a small increase in dv. So again, we have the same argument as what we had earlier. So if we had y equals u over v, we can say that's the same as maybe we increase y a little bit. So we have y plus delta y, which equals u plus delta u all over v plus delta v. Okay, so then we can say, right, if we know what this is equal to, we can say that d delta y equals u plus delta u over v plus delta v minus our y from here, which is minus u over v. And then if we multiply this out, we can say that delta y therefore equals u delta u minus v, minus v delta v all over, multiply at the bottom, v plus delta v. I'll close brackets. So we then, if we were to divide all this through by x, if we wanted to find what it would be with respect to x, we can say that delta y by delta x would be equal to v delta u by delta x minus v delta v by delta x. We put that on the bottom. We're dividing this all through by v uh, brackets v plus delta u, delta v, sorry. And then if we tidy this up, we can now say that dy, or delta y, by delta x is equal to v delta u by delta x minus v delta u by delta x, all divided by v squared plus delta v, v delta v, multiplied by v delta v. So we know that all these things, as we approach infinity, get smaller and smaller, as we previously said. So therefore, we can say that dy by dx is equal to v du by dx minus u dv by dx all over v squared. And this becomes our product rule. So what we'll do now is we'll actually just show how it works with a quick example. So what we can say is, if we have an example of maybe something y equals 4x minus 3 to the power of 6, and we're dividing this by x plus 2, and we're asked to find dy by dx. Well, we can say that u equals 4x minus 3 to the 6, and we could say that v equals x plus 2, and then we can find our du by dx and our dv by dx, and that would equal then, so we have a 4 inside, so 4 multiplied by 6, bring it down to bring the power down, so we get, that would be 24, 4x minus 3 to the power of 5, and if we just differentiate this, we get a simple 1. So we use our formula, which says dy by dx is equal to v delta u by dx, sorry, minus u dv by dx all over v squared. and we stick our numbers in, we're going to find out that that's going to give us v. So u delta u, which will be x plus 2 times by delta v multiplied by 24, 4x minus 3 to the 5, minus our 1 multiplied by 4x minus 3 to the power of 6. This is all going to be divided by v squared, which is x plus 2 squared. And we can start to neaten that up a little bit, where we take some factors out, and what we would get, that would be 4x minus 3 to the power of 5, 20x plus 51 all over x plus 2. So that is the answer to our differential, and we could x plus 2 so squared. So what we could do, what we've done now is we've created a function. It's quite a complex function, but if you were then to try and solve something, you were trying to look at a really complex curve. Again, what we could do is we could use the same tools what we've used previously in differentiation. If we were to set this towards 0, we could solve for 0 to find the roots, but to solve for 0, we might have to use the Newton-Raphson method in this case. So we've now got a tool set which we can use simple functions to describe a curve. We can now look at complex functions. We can find the curves. We could also then take the second differential to find out if these points which were turning inside of these curves were maximum or minimum turning points, and we could solve for x as well. So that's been calculus. That's been a little bit more difficult of calculus. Calculus goes on and on and on and on. So if you're interested, potentially there'll be some more modules later through your university career. So next we're going to move on to some statistics in the next few lectures, but I'll leave that there just with calculus.